Having defined invertible matrices and having discussed the main algorithm for finding inverses of square matrices, let's discuss a little bit how we can recognize an invertible matrix in some special cases. So most of the time, it's not easy to tell right away by just looking at the matrix whether the matrix will be invertible or not, but sometimes it is not difficult to see. So what are some of the properties of an invertible matrix? So a matrix A is invertible if elimination produces a full set of pivots. What that means is that if the matrix is of size n by n, we need n pivots. Otherwise, elimination will produce a row of zeros. So maybe I should say if a matrix does not have a full set of pivots, then elimination will produce a row of zeros. Importantly, a row of zeros tells us that the rows and the columns of the matrix are linearly dependent. So a row of zeros so this is really in a square matrix. Implies that the rows and the columns of A are linearly dependent. And remember, we said that when the columns of a matrix are linearly dependent, then that matrix must be singular. Singularity for a matrix or invertibility only makes sense if the matrix is square. If the matrix is not a square matrix, we can talk about columns being linearly dependent or linearly independent, but to label a matrix as singular or invertible in the case when it is not square doesn't make much sense. All right, so let's look at some examples of invertible matrices. Or rather, matrices where it's really easy to tell whether the matrix is invertible or not. So such a matrix is a triangular matrix. And so a triangular matrix is easy to determine whether it's invertible or not, but the test for invertibility really is whether or not the diagonal, if there are any diagonal entries that are zero. So because I wrote here examples of invertible matrices, this would be a triangular matrix with no zero terms along the diagonal. Let me write an example or two. So one example could be, say this L for lower triangular, 1, 3, 4, 0, 1, 5, 0, 0, 1. You see here, the pivots are 1, 1, and 1. This is a lower triangular matrix. We normally don't determine pivots before we have done elimination, but on a triangular matrix, we know that the pivots really are the entries along the diagonal. Let's find the inverse of this matrix and see what we get. So I'm going to place this matrix in an augmented matrix with the identity on the right-hand side. Now, the first pivot, as we noted, is the first non-zero term of the first row. I'm going to carry out elimination of both terms under the pivot simultaneously. So I will have row 2 minus 3 row 1 into row 2, and row 3 minus 4 row 1 into row 3. What I get is the first row stays unchanged, 1 0 0, and then 1 0 0 in the augmented matrix. Then I have 3 minus 3, which is a 0, 1 minus 3 times 0, that's a 1. The 0 stays unchanged. Then we have 0 minus 3, so that's a negative 3. And then 1 0, those remain unchanged. Then we have 4 minus 4, that's a 0. 5 minus 4 times 0, that's a 5. 1 minus 4 times 0 is a 1. Then we have 0 minus 4, that's a negative 4. 0 minus 4 times 0 is a 0, and then the 1 also stays unchanged. Now that we have eliminated under the first pivot, we want to eliminate under the second pivot. Now, before I continue, observe that the changes that we saw in this right-hand side matrix are really located just here in the exact same location where we wanted to eliminate in the original matrix L. And that makes total sense because that's where we are carrying out the changes with the identity matrix as well. All right. The new operation for elimination is R3 minus 5R2 into R3. We apply that on both matrices, and we get. So the first two rows stay the same. I'm just going to copy them down. 0, 1, 0, negative 3, 1, 0. And then I know I need to get here 0, 0, 1 because that was the whole point of writing the operation. And then I have row 3 minus 5 times row 2. So that's negative 4 plus 15. That will be 11. And then I have 0 minus 5. So I have a negative 5. And then I have 1 minus 0, which is 1. So you see on the left-hand side, I got the identity matrix, which means that on the right-hand side, I have L inverse. So this over here is L inverse. And what is interesting is that whenever you have a lower triangular matrix, especially with ones along the diagonal, then its inverse will be of the same shape. It will also have ones along the diagonal, and the non-zero terms will be under the diagonal. So the inverse of a lower triangular matrix is lower triangular. Let me write that. The inverse of a lower triangular matrix L is also lower triangular. And as you might imagine, the inverse of an upper triangular matrix U, for example, is also upper triangular. Now note that not all diagonal matrices will be invertible. Not all triangular matrices will be invertible. The test is whether or not there are zeros along the diagonal. If there are zeros, then the matrix is definitely not invertible. All right, now the same goes for diagonal matrices because the diagonal matrix is both upper triangular and lower triangular. So the inverse of a diagonal matrix, which we've already discussed, is again a diagonal matrix. Now, I want us to look at some examples of invertible matrices or recognizing them just by looking at the matrix in terms of linear dependence. So, observations of linear dependence will tell us, can be useful to tell us whether or not a matrix is invertible. So here's some examples. Let's look at this matrix. It's a 2 by 2 matrix with coordinates 4, 8, 3, 6. Now, what do we see? We see that the first row and the second row are linearly dependent because the second row is 2 times the first row. So we have row 2 equals 2 times row 1, which means that if we were to carry out elimination, we will get a row of zeros. Now, is it true that the columns are also linearly dependent? Well, you see that the the second component in each column is 2 times the first component in each column, which means that the vector 4, 8 is 4 times the vector 1, 2, and the vector 3, 6 is 3 times the vector 1, 2. So yes, indeed, they are linearly dependent because both are multiples of the same vector. So if we were to represent them geometrically, they would lie on the same line. So we conclude right away that the matrix is singular or not invertible. That's the same meaning. All right, now what about the following matrix? We have 4, 3, 8, 7. When you have a 2 by 2 matrix, you can tell whether the matrix is invertible by just seeing if one vector is a multiple of the other, whether you look at the columns or you look at the rows. Well, we had a very similar matrix on how, just on the left, we see that here elimination will not be a problem. If we were to carry out elimination, trying to eliminate under 4, we would have R2 minus 2R1 into R2, and this would give us 4, 3, 0, 1. We reach an upper triangular matrix which is invertible because both pivots are non-zero. So we know that this matrix will also be invertible. Of course, this is not the way to find the inverse. To find the inverse, we would actually have to augment the identity matrix, but we already know that the matrix is invertible. And perhaps I should mention here that the main reason is that these elementary row operations do not change the invertibility or the singularity of the matrix. On the contrary, they preserve it. So elementary row operations preserve invertibility or singularity. So if a matrix was singular, it would continue to be singular after applying the elementary row operation. And if it was invertible, it would continue to be invertible. Now, what about this next example? We have 6, 6, 6, 0. If you look at this example, you cannot call this a triangular matrix, although it does look very, very similar to a triangular matrix. If we just exchanged the two rows, we would get a lower triangular matrix, and that matrix would be invertible. And since row exchanges are a type of elementary row operation, they would not affect anything. But also we can just by observation see that the two rows are indeed linearly independent, because you cannot produce a zero or a non-zero from a zero. You cannot multiply the second row by anything to produce the first row, and vice versa. So here we have the rows or the columns, whatever you like to focus on, are linearly independent. So the matrix is invertible. Let's look at another matrix. The matrix of all, a 2x2 matrix of all sixes. The first two rows, or the two columns, however you want to see it, they're exactly the same, which means they are linearly dependent, which means the matrix is not invertible. And now let's look at two 3x3 matrices. We have the matrix 1, 1, 1, 0, 1, 1, 0, 0, 1. We actually have seen this matrix. This is a summation matrix that we saw in the very first couple of videos. It is a lower triangular matrix with the pivots along the diagonal all being non-zero. So we know that this matrix is in fact invertible. So let me write lower triangular with all entries along the diagonal being non-zero. So that immediately tells us the matrix is invertible. And the last example for this video, we'll look at 1, 1, 1, 1, 1, 1, 1, 0, 1. So this matrix is not upper triangular, it's not lower triangular. Our best hope is to look for some form of linear dependence of the rows or of the columns. So you see here that the first row equals the last row. That immediately tells us linear dependence or non-invertibility or singularity. And the first column equals the second column. So both of these things say that the matrix is singular. All right, I hope with this you are a little bit feeling better about these invertible matrices and how they can tell us something about linear dependence and linear independence. So just like we used linear dependence or independence of rows or columns to tell us whether a matrix is invertible, we could also use Gauss-Jordan elimination to tell us if a collection of vectors or column vectors is independent or dependent. If you would just take those vectors and put them as columns of a matrix, then start carrying out elimination, this would be a method to tell us whether that collection of vectors is dependent or independent. We will revisit that concept in upcoming videos.